Assalamu alaikum. This is our 24th lecture of managerial economics, and the topic that we are considering these days is linear programming. In our previous two lectures on linear programming, we have considered maximization problem, minimization problem, and we have solved these problems using both the graphical method and the algebraic method. Today we are going to concentrate on the dual problem, which is the dual of the primal problem. Given a linear programming problem, it has its dual problem, which is a symmetrical or corresponding problem. Today we will be considering the meaning, formulation, solution and advantages of the dual problem. Every maximization problem has a dual problem, which is a minimization problem, and every minimization problem has a dual problem, which is a maximization problem. From the viewpoint of economics, the production decisions, they gives us the optimal solution of resources, that is the optimal allocation of the given resources. This objective can be achieved by minimizing the shadow prices or the opportunity cost of the inputs which are available to the firm, and these inputs obviously are scarce resources which are available to the firm. So from the mathematical point of view, on the other hand, it is the same objective can be achieved by solving a second linear program, which is called the dual. The dual of the problem, that is the dual of the original primal problem, is if we look at the solution of both of these two, we will see that there are many similarities and differences in the solution formulation of the primal and the dual problem. As far as the primal problem is concerned, basically this problem is related to the operational type of decisions, that is what quantities, that is to determine what quantities of each product is to be produced. On the other hand, dual focuses on the resources. So this means that rather than focusing on the product or product mix, dual focuses on the resources. And once the dual is solved, we can see that it reflects the true impact of the scarcity of these resources. The solution to a dual program is the solution of shadow prices. I have mentioned this term earlier, shadow prices. Now, what is meant by a shadow price? A shadow price is the change in the value of the objective function per unit change in the input or the constraint of the primal problem. This means that given a maximization problem, the shadow prices will tell us how much the profit would increase per unit increase in the use of an input which is related to a constraint. So हमारे पास inputs हैं, जैसे कि हमने maximization problem में देखा था. We have inputs A, B and C, and these inputs could represent labor, capital and raw materials, and there we have seen that we have maximized the objective function subject to these constraints of inputs. Here we are going to solve the shadow prices, that is what will be the shadow price of these inputs. तो शेडो प्राइसेस जो हैं उससे हमें पता चलता है कि जो स्केर्स रिसोर्सेज हैं ए, बी एंड सी, उसका जो है उसको हमने वहाँ पे मिनिमाइज करना होता है अगर प्राइमल प्रॉब्लम जो था वो मैक्सिमाइजेशन प्रॉब्लम था. So in this case we can see that we can consider the shadow prices as the marginal valuation or the opportunity cost of the inputs which are available to the firm. If an input or resource is not fully employed, then its shadow price is equal to 0. Previously in solving a primal problem, we have seen that when a resource is not fully employed, this means that its constraint is non-binding, and there we have said that the slack corresponding to this constraint is non-zero. जैसा कि हमने अपने maximization problem में देखा था that we have three inputs A, B and C, and in the optimal solution we have seen that the slack variables of input A, input B were equal to 0, which means that these two constraints were binding constraints, whereas the third constraint, which was for input C, that was non-binding. Why? Because the input C was not fully employed. there were 21 units of this input. They were available to the firm, and only 12 of these were utilized. This means 9 units of this input C were remained unutilized, वो use नहीं हुए. तो इसलिए यहाँ पे हमने कहा था that the slack variable for input C, that is SC, was equal to 21 minus 12, that is 9. Whereas the slack variables of the other two inputs A and B were equal to 0. So this means that in that case, in that problem, the first two constraints for input A and B were binding, और वहाँ पे उनकी जो slack variables थे, they were equal to 0, whereas their shadow prices will be non-zero, or positive non-zero. In the case of third constraints, that is for the input C, वहाँ पे हमने देखा था कि उसके कुछ units जो थे वो utilize नहीं हुए थे. तो इसका मतलब ये है कि वहाँ पे स्लैक मौजूद था, एंड देयर वाज अ स्लैक ऑफ 9 यूनिट्स. 9 यूनिट्स जो थे वो उस इनपुट के इस्तेमाल नहीं किए गए थे. सो दिस मीन्स दैट इफ the firm now increase this input, it would leave the value of the objective function, that is the profit, unchanged. इससे profit पे कोई असर नहीं पड़ेगा अगर firm जो है इस input को increase करेगी, which is presenting a non-binding constraint, and it has already been not used. There are some of its units which have remained unused. तो इसलिए ये जो यहाँ पे जो input C थी, its price was, its shadow price was equal to 0. This means that a firm should increase an input as long as its shadow price is equal to or larger than the cost of hiring this input or purchasing this input. When we say that the firm can increase an input, we are saying, in other words, that it can increase labor, capital, or raw materials, and obviously the firm has to pay prices for it. Prices in the form of, for labor it has to pay wages, for capital it has to pay the rental price, and for raw materials obviously it has to pay the market price. So firm जो है उसको अगर वो अपनी inputs को increase करेगी तो इसके लिए उसको cost जो है incur करनी पड़ती है in the form of wages, rental price, and prices of the raw material. So in this case, we are saying, what we are saying here is, if the shadow price of a resource is equal to 0, then the firm should not increase that input. If on the other hand, the shadow price of a particular input is non-zero, then the firm can increase that input as long as its shadow price is larger than or equal to the cost of hiring or purchasing that input. The solution of dual is very important. Practically, it has a great importance for the managers, for the executives, business executives. The reason is that it gives knowledge to the manager, to the decision makers, that if the shadow price of such and such particular input is non-zero, then the firm can increase its net profit by increasing that particular input. If on the other hand, the shadow price of a particular input is equal to 0, then the firm should not increase that particular input, because it will not affect the net profit of the firm. तो इसमें जो operational decisions हैं यहाँ पे फर्म के, उसमें फर्म को एक्सपेंशन जो है, उस जो डिसीजन है कि प्रोडक्शन इंक्रीज़ करनी चाहिए, तो उसमें कौन सी जो इनपुट्स हैं उनको इंक्रीज़ करना है और कौन सी इनपुट्स हैं जिनको इंक्रीज़ नहीं करना है, उसमें जो डुअल है इट हैज़ अ ग्रेट प्रैक्टिकल इम्पोर्टेंस, क्योंकि यहाँ पे क्रूशियल जो डिसीजन है वो फर्म को लेना है, which inputs are to be increased and which inputs are not to be increased. So in that sense, it becomes very important for the firm to solve the dual of a given problem. As far as the solution of the dual is concerned, there we can see that we can solve using the same procedure, क्योंकि हम इसको graphically भी solve कर सकते हैं, algebraically भी solve कर सकते हैं, and also we can use the computer software. As far as the computer software is concerned, there we can see the printout of the computer software. It gives not only the solution if you are solving initially the primal, then the solution which is given by the computer, it includes not only solution to the primal but also to the dual. उसमें जो है sensitivity analysis, shadow prices of the inputs, this information is completely entirely given in the when we are using the computer software. लेकिन यहाँ पे जो है हमने ग्राफिकल मेथड यूज़ किया था और इस तरह से हमने algebraic मेथड यूज़ किया था corner point solutions. So if we solve using these two methods, that is, if we solve the primal, we can also give the results of the dual problem. इसी तरह से अगर हम dual को जो है solve करेंगे तो इसके लिए हम जो primal है उसके ज़रिए से solve कर सकते हैं. That is, we can say that we can solve dual via the primal and primal via the dual. जो अगर हमें एक प्राइमल प्रॉब्लम दिया हुआ है तो इसको हम डुअल में किस तरह से ट्रांसफॉर्म करेंगे. देयर आर सर्टेन रूल्स फॉर इट एंड दीज रूल्स आर, you can see rules of transforming a primal into a dual. The first rule here is that the optimization, the sense of the optimization is reversed. That is, if it is initially the primal problem is that of a maximization problem, then the dual will be a minimization problem, and vice versa. The second rule is that the inequality constraints, their sense of direction, their direction of the inequalities is also reversed. Obviously, when we have said that the first rule is to reverse the optimization, तो अगर आपके पास जो initially primal problem था, that was a maximization problem, and now it is transformed into a minimization problem. इसको हम reverse कर देंगे. तो इसमें जब हमारे पास अगर maximization problem था तो इसके जो constraints थे, they were of the form equal to or less than. But now we are saying that the optimization is reversed. Since the optimization is reversed, therefore the sense or the direction of the inequalities will also be reversed, so that initially if it is of the form equal to or less than, then it will be transformed into equal to or greater than. तो इस तरह से सारे जो अगर सब if all the constraints are of the form less than or equal to, they will be transformed, they will be reversed as equal to or greater than. The third rule is that all the coefficients which appears in the set of constraints for a primal problem, we take a transpose of that coefficient matrix. If we express it in the matrix format, then the coefficient matrix जो यहाँ पे हमारे पास constraints में जो coefficient matrix है उसका हम transpose लेंगे dual problem में. ये जब हम problem जो है इसको हम numerically इसको solve करेंगे तो यहाँ पे ज़्यादा clear हो जाएगा. Next rule is that the row vector of the coefficients of the primal problem, it is transposed into the column vector of constants of the dual problem. This in other words means that the number of choice variables in the primal problem is always equal to the number of constraints in the dual problem. Similarly, the next one is that the column vector of constants in the primal problem is transposed into the row vector of the coefficients of the objective function in the dual problem. Again, we can say that the number of constraints in the primal is always equal to the number of choice variables in the dual problem. Next is that the set of choice variables, if the choice variables in the primal are expressed as let's say x1, x2, x3 and so on, in the dual problem these are replaced by y1, y2, y3 and so on. But it's not necessary that we use these symbols, we can use any other symbols. Lastly, we can see from these formulation or from these transformation principles or rules, we can see that easily here we can conclude that the dual of a dual is the primal itself. It's very simple. If we have a primal problem and we formulate its dual problem, if we now again find the dual of that dual, we end up with the primal problem. In the next slide, now we are going to show you how to transform a primal problem into a dual problem using the rules that we have just now described. Now look at the screen. The primal problem is that of maximization, that is, we have to maximize the objective function c1x1 plus c2x2 plus c3x3. Obviously, the optimization is reversed in the dual problem, and now we have to minimize the cost function, which is equal to R1 y1 plus R2 y2, subject to a set of constraints which where you can see the inequality direction is equal to or less than, and in case of the set of constraints for the dual problem, this direction is changed, that is now it is equal to or greater than. The non-negativity constraints are retained because we are saying that we are not considering negative inputs or negative outputs, and for the case of dual similarly we are not considering negative shadow prices. अब अगर आप स्क्रीन पे देखते हैं तो हमारे पास जो ऑब्जेक्टिव फंक्शन है वो हमने किस तरह से डुअल का ऑब्जेक्टिव फंक्शन हमने किस तरह से फॉर्मुलेट किया है. We have said in our rules that the column vector of the coefficients of objective function in the primal, it is transposed into the column vector of constants in the dual problem. So C1, C2, C3 is a row vector which is now transposed into C1, C2, C3 as the right hand constants of the dual problem. Now look at the objective function of the dual, which is equal to C equal to R1 y1 plus R2 y2, and we have said in our rules, we have explained that the right hand side constants, the column vector of constants in the primal problem, it is transposed into the row vector of the coefficients of the objective function. So in the column here in the primal problem, the column vector of constants was R1 R2. Now this is transposed into a row vector of the coefficients of the objective functions R1 R2. Similarly, the set of constraints, look at the set of the constraints of the primal problem. Here the coefficients are A11, A12 and so on for the first constraint, and for the second constraint you can see that these coefficients are now we take the transpose of these coefficients, that is rows and columns are interchanged and the non-negativity constraints are retained. In case of the dual problem, now our choice variables are y1 and y2, and these choice variables are presenting what they are presenting, the shadow prices of the fixed quantities of the resources, that is R1 and R2. Next, in our primal problem, we have converted, in order to find the algebraic solution, we have converted our inequality constraints into equations by adding slack variables if it is a maximization problem, and by subtracting surplus variables if it is a minimization problem. Since in our primal problem we have a maximization problem, so we convert it into equations by adding the slack variables, and here we have two constraints. We add SA or S1 to the first constraint and S2 to the second constraint, and we convert the inequalities into the equations. Similarly, in case of dual, since it is a minimization problem, we subtract the surplus variables from each of the constraints, and we convert these constraints from inequalities to equations. Now, solving a dual problem, we use these rules, that is, we first of all formulate a dual, and then we also use the duality theorems. Here we are going to consider two duality theorems, that is duality theorem 1 and duality theorem 2, which has two parts, further two parts, that is part A and part 2. On screen you can see the duality theorem 1, and here we can see that the duality theorem 1, the statement is the optimal values of the primal and the dual objective functions are always identical, provided that optimal feasible solution do exist. That is, the maximum value of the primal, if it is a profit maximization problem, equals the minimum value of the dual cost minimization problem. So here we can see that the optimal values of the objective function, both for the primal and the dual, they are identical. but the condition is that the optimal solution exists. Obviously, if we are solving, if we have solved, let's say, a primal problem and it has a unique optimal solution, only then we can say that the dual will have a unique optimal solution. Otherwise, recall from our previous discussion, we have said that it is possible that no unique solution exists. वहाँ पे हमने देखा था कि 3 situations could arise where we cannot find the optimal solution of a given problem using linear programming technique. और इसमें possibilities थी. Number 1, there was an infinite number of optimal solutions. There was an infinite number of solutions due to the reason that one of the constraints and the objective function has the same slope. The other possibility was that the solution was unbounded. That is, the value of the objective function was unbounded. Profit was increasing, profit might be increasing indefinitely or cost might be decreasing indefinitely. Practically ये problem जो है वो हम face करते हैं ज़्यादा मैक्सिमाइजेशन प्रॉब्लम में. और एक तीसरी सिचुएशन हमने डिस्कस की थी जिसमें कि where the region of feasible solutions is not defined. There we have seen that it is no more a convex set, therefore the solution to the problem does not exist. If one of these possibility arises, then obviously the solution will not be possible. And if we cannot solve a linear program, that is the primal program, we can also we cannot solve the corresponding dual problem. Next, you can see the duality theorem 2. The statement of the duality theorem 2, it has 2 parts, and this statement says that if a certain choice variable in a linear program is optimally non-zero, then the corresponding dummy variable in the counterpart program must be optimally zero. अब इसको हमने जो है we have said that if the choice variable is of a program is optimally non-zero, its corresponding slack variable or dummy variable, क्योंकि collectively slack variables and surplus variables are collectively called dummy variables. So in that case, its corresponding dummy variable in the counterpart program, it will be equal to 0. In symbols, we can express the same as if I is greater than 0, this would imply that Si is equal to 0. Now if the ith choice variable of the dual problem is non-zero, it is greater than 0, then its corresponding slack variable, that is the ith slack variable in the optimal solution, will be equal to 0. Or we can say that if xj is greater than 0, this will imply that tj is equal to 0. If the jth choice variable in the primal problem is non-zero, then its corresponding slack, which is jth variable, jth slack variable or surplus variable, या हम collectively dummy variable कहते हैं, the jth dummy variable will be equal to 0. The second part says, if a certain dummy variable in a linear program is optimally non-zero, then the corresponding choice variable in the counterpart program must be optimally 0. In symbol, this can be explained as if the ith slack variable or ith dummy variable optimally is non-zero, then its corresponding choice variable in the dual problem must be equal to 0. या फिर जो है इसको हम इस तरह से भी कह सकते हैं that if the jth dummy variable is greater than 0 optimally, if it is greater than 0, this would imply that the jth choice variable of the primal problem will be equal to 0. Well, this duality theorem 2 is also called complementary slackness, and this can also be explained as you can see in on the screen in the next slide. Complementary slackness जो है, that is given as, suppose that x is x1, x2, xj primal feasible, and that y is equal to y1, y2, yi is dual feasible, and let their corresponding slack variables, primal slack variables are s1, s2, si, and let t1, t2, tj denote the corresponding dual slack variables, then x and y are optimal for their respective problems if and only if xj tj is equal to 0 for j equal to 1 to n, and si yi is equal to 0 for I equal to 1 to m. This is what is called complementary slackness. Here the main variable is the choice variable, or it is called main variable. The product of the main variable and the corresponding slack variable in the counterpart program, the product of these two is equal to 0. Why? The reason is that we have said that if optimally the choice variable is non-zero, then its corresponding slack variable will be equal to 0 in the counterpart program. So obviously when one of the component of the product is equal to 0, then the product will be equal to 0. Similarly, we are saying that xj tj is equal to 0 and si yi is equal to 0. The product, these products are 0, as I explained earlier, कि अगर आपका main variable, that is the choice variable, is optimally non-zero, then its corresponding slack variable in the counterpart program will be equal to 0. If on the other hand the slack variable optimally is non-zero, then its counterpart, then its corresponding choice variable or main variable in the counterpart program will be equal to 0. So this is called complementary slackness. अब जो है ये duality theorems जो हमने explain किए हैं, that is the duality theorem 1 and 2. With the help of these duality theorems, you can see that it becomes clear that if we know the solution of one program, we can easily solve the other program. That is, we can say that we can solve the dual via the primal, or we can solve the primal via the dual. If we अगर हम initially जो है primal को solve करते हैं, तो हम dual की values जो हैं उसकी solution भी हमारे पास आ सकती है, हम मालूम कर सकते हैं using these duality theorems. So using these duality theorems and the rules that we have used to transform one program to the other program, using these two, we can easily find the solution of one problem by solving the other problem. And it is beneficial, that is, it has its advantages. Here we can see on the next screen the advantages of the dual. From the duality theorems, it is clear that the solution of one program provides full solution to the other. This is beneficial because number one, it enables us to solve a minimization problem in terms of maximization. And we know that the maximization problem is relatively easier to solve. And the second advantage of the dual is that for primal with 3 decision variables, the dual reduces the program to 2 decision variables, which can be solved graphically. If your primal problem involves 3 choice variables and 2 constraints, then the dual program is reduced to 2 choice variables and 3 constraints. जब आपके पास choice variables जो हैं वो 2 हो जाएंगे instead of 3, you can solve it graphically, because the primal cannot be solved easily graphically since it has 3 choice variables and it is difficult to draw a 3-dimensional diagram and interpret a 3-dimensional diagram. Even if both problems are non-graphable, that is, both primal and dual has more than 2 choice variables, in that case, if the primal is a minimization problem, we should go for the dual problem. यानी कि हमें बजाय इसके कि हम मिनिमाइजेशन प्रॉब्लम को सॉल्व करें, हम इसका डुअल जो है वो फॉर्मुलेट करेंगे और मैक्सिमाइजेशन प्रॉब्लम को सॉल्व करें, क्योंकि जैसे मैंने पहले कहा, मैक्सिमाइजेशन प्रॉब्लम इज रिलेटिवली इजियर टू सॉल्व देन द मिनिमाइजेशन प्रॉब्लम. In the next slide, we are going to consider a specific numerical example which we have already considered while discussing a linear programming problem, जहाँ पे हम इसको maximization problem जो है ये हमने consider किया था. And you will recall that we have solved this problem both graphically and algebraically. Now we are going to solve the same problem by transforming it. First we will transform it into its dual and we will solve the dual, and then we will compare the results. So यहाँ पे आप स्क्रीन पे देख सकते हैं primal problem हमारे पास है maximize. Here we can see that we have the primal problem and we have to maximize the objective function pi equal to 12x plus 9y, and this is subject to 3 constraints of inputs a, b and c, and the non-negativity constraints where x, y, the choice variables, are both equal to or greater than 0. The corresponding dual problem is here. You can see that obviously the optimization will be reversed, and now we have to formulate our objective function, which is minimize C equal to 32 VA plus 10 VB plus 21 VC. Now, what is VA, VB and VC? These are the shadow prices of the inputs A, B and C respectively, and these shadow prices of the inputs are to be multiplied by the fixed quantities of inputs A, B, C which were available to the firm, so that our objective function in this case C is the total cost of imputed values of the shadow prices, imputed values of these fixed quantities of the inputs A, B and C which were available to the firm. And we can see in the primal problem these fixed quantities were 32 for input A, 10 for input B and 21 units for input C. So यहाँ पे हमारे जैसे कि हमने rules में अभी आपको बताया था that the column vector of constants of the primal they are transposed into the row vector of the coefficients of the objective function, so that our coefficients of the objective function for the dual are now 32 VA plus 10 VB plus 21 VC, where we have said that VA, VB and VC are the shadow prices of these inputs, and the purpose or the objective of this dual problem is to minimize these shadow prices subject to the constraints. Now, what is the implication of these constraints of the duals? Look at the constraints. You can see that constraint A is 4 VA plus VB is equal to or greater than 12, and constraint B is 2 VA plus VB plus 3 VC is greater than or equal to 9. यहाँ पे जो हमने ट्रांसफॉर्मेशन की है, let me explain it first. Here the set of, look at the primal problem, and you can see that in the primal problem the coefficients of the constraints are the first constraint 4, 2, 1, 1, 0, 3. तो फर्स्ट कंस्ट्रेंट के जो कोएफिशिएंट्स हैं 4, 2 हैं, सेकंड के 1, 1 है because x y means 1x 1y, and for the third constraints we have no x which means 0x plus 3y. So उसके जो coefficients हैं वो हमारे पास हैं 0, 3. All these rows of coefficients are now transposed into columns. Okay, and in the maximization problem the coefficients are 12 and 9. And what does this 12 and 9 indicates? These were, as we have explained earlier, that these coefficients of the objective function in the primal are the per unit profit contribution of product X and product Y. And these coefficients, the column vector of these coefficients are transposed into the column vector of the right hand side constants of the dual program. तो वो आप देख सकते हैं कि यहाँ पे हमारे पास dual program के जो constants हैं, they are the column vector 12 and 9. The non-negativity constraint, as I said earlier, they are retained, and we assume that all the variables, choice variables of both the primal problem and the dual problem, they are equal to or greater than 0. That is, all of these are non-negative. Well, now looking at the constraints, what is the implication of these constraints? Constraints को हम इसकी economic reasoning जो है, जो अभी मैंने आपको technical उसका जो था reason बता दिया, that how we have actually transformed a primal problem into a dual problem. But what is the economic implication or the economic reasoning behind it? We have already explained the objective function, that it is the total imputed cost of the fixed quantities of the inputs A, B, C which were available to the firm. And now looking at the constraints, that is the set of constraints, look at the first constraint first, which says that 4VA plus VB is greater than or equal to 12. This means that 4 units of the input A is used to produce 1 unit of product X, plus 1 unit of input B is used to produce 1 unit of product X, and these are multiplied, these quantities, that is 4 and 1, are multiplied by the shadow prices of these inputs. So we can say that the first constraint is the sum of the products of the shadow prices multiplied by the quantities of inputs which are required to produce 1 unit of product X must be equal to or larger than the profit contribution, per unit profit contribution of product X. Now we are going to solve the dual problem. From our solution of the linear program, that is the primal problem, we know that the constraint C was a constraint which was not fully, the input C was not fully utilized. So constraint C was non-binding, and there we have seen that the slack variable was equal to 9. That is, out of 21 units of input C, 9 were remained unused. So this means, this in other words means that we have already said that when the constraint is of an input is non-binding, that implies that its shadow price is equal to 0. This means that VC, which is the shadow price of input C, is equal to 0. So setting VC equal to 0, solving these constraints simultaneously, we have 4VA plus VB equal to 12, and we subtract the second constraint from the first constraint, so that we get 2VA equal to 3, or VA is equal to $1.5. And now substituting this value of VA into either the first constraint or the second constraint, we get the value of VB, that is the shadow price of input B, which is equal to $6. So जो VC है that is equal to $0, because we have seen that it's a constraint. Input C is non-binding constraint. This means if we increase input A by 1 unit, this would increase the profit of the objective function, which was previously equal to $108. This will increase the profit by $1.5. And similarly, if input B is increased by 1 unit, this will increase the profit by $6. If on the other hand input C is increased, since its shadow price is equal to 0, therefore this will leave the net profit unchanged. अब आप इस solution को जो हमने अभी यहाँ पे derive किया है, that is we have derived the shadow prices of input A, B and C. Substituting these shadow prices of input A, input B and C into our objective function of the dual problem, we get, we solve it and we simplify it, and we get the answer which is equal to $108. हमने ये प्रॉब्लम पहले भी सॉल्व किया था, जैसे कि मैंने अभी आपसे कहा कि ये जो मैक्सिमाइजेशन प्रॉब्लम था, तो उसमें आपको याद होगा कि हमारे पास जो इसका ऑब्जेक्टिव ऑप्टिमल सोल्यूशन आया था, that was also equal to $108. That is, we have solved the problem both graphically and by using the algebraic method, which is the corner point solution. तो उसमें हमारे पास रिजल्ट जो था, जो मैक्सिमम प्रॉफिट जो था, हाईएस्ट प्रॉफिट, that was equal to $108, and we have said that by using product mix of x equal to 6 and y equal to 4, the firm maximizes its profit, which was equal to $108. And here, as we have said in duality theorem 1, that the value of the objective function for both the primal and the dual is exactly the same, that is identical. So here we can see that the cost is minimized, which is also equal to $108. That is, here the shadow prices of the given constraints or the inputs is minimized, which is equal to $108. Now by substituting these values of that is the shadow prices of VA equal to 1.5, VB equal to 6 and VC equal to 0 into our constraints, we can establish here that the slack variables for the input A and input B are equal to 0. So यहाँ पे आप देख सकते हैं first constraint 4 multiplied by 1.5 VA plus 6 plus SA, that is the slack variable, equal to 12. So we convert this inequality constraint into an equation by adding a slack variable, and similarly by adding a slack variable to the second constraint we convert it into an equation, and when we simplify it we can see that both SA, that is the slack variable of input A, and this SP, that is slack variable associated with input B, are equal to 0. अब यहाँ पे हमने ग्राफिकल सोल्यूशन जो है, क्योंकि हम ये हमारा जो ड्यूअल प्रॉब्लम था, दिस वाज इन्वॉल्विंग 3 चॉइस वेरिएबल, सो वी हैव नॉट सॉल्व्ड इट ग्राफिकली। लेकिन कॉर्नर पॉइंट्स जो हैं वो हम इजीली फाइंड आउट कर सकते हैं। एज आई सेड अर्लियर दैट कॉर्नर पॉइंट्स कैन बी obtained by solving the two constraints simultaneously. We can get the corner point, and similarly we can get the corner points which is the result of an intersection of one of the axes, that is either the horizontal x or the vertical x, and one of the constraints. So इस तरह से ये जो corner points हैं वो हमने यहाँ पे show किए हैं column 1 में, and these corner points are numbered as 1 to 5. And in the next 3 columns we have shown the shadow prices of input A, B and C, and the corresponding surplus variables which are given as T1 and T2. और जो लास्ट में कॉलम है उसमें हमने कॉस्ट जो है, इनकी imputed cost जो है वो शो की है. So you can see here the first point where VA is equal to 0, VB is 0, that is the point of origin, and here T1 and T2 are negative values, so we reject this solution because we have said that we are not going to consider negative shadow prices, और इसके बाद या नेगेटिव जो स्लैक वेरिएबल्स हैं वो हम कंसिडर नहीं कर रहे. फिर सेकेंड पॉइंट पे VA is 0, VB is 12, while VC is 0 and the result is $120. इसी तरह से जब हम इनको कंपेयर करेंगे तो आप देख सकते हैं that the last point where the shadow price of input A is 1.5, the shadow price of input B is 6, and the shadow price of input C is 0. There the cost is minimized and it is equal to $108, जो कि हमने पहले ही आपको कैलकुलेट करके अभी बताई थी. सो इन पॉइंट्स को अगर हम कॉर्नर पॉइंट्स को अगर हम कंपेयर करते हैं तो यहाँ पे भी हम देख सकते हैं कि जो लोएस्ट कॉस्ट है दैट इज अगेंस्ट आवर ऑप्टिमल सॉल्यूशन व्हिच वी हैव ऑलरेडी फाउंड. As I said earlier that given the solution of one problem we can completely find the solution of the other problem, that is given the solution of the dual problem we can easily find the solution to the primal problem, or the other way around, if we have solved the primal problem first we can easily find the solution to the dual problem. In this case now we have found the solution to the dual problem, we can easily find the solution to the primal problem by using the duality theorems and the rules that we have used to transform one program to the other program. Now by using the duality theorem, obviously the first duality theorem says that the values of the objective function for primal and the dual are identical. So यहाँ पे हमने पहले आपको कैलकुलेट करके बता दिया है कि that in both cases we have seen that the profit maximum profit was equal to $108, optimal solution जो हमने find out किया था, और यहाँ पे भी it is the minimum cost, the cost is minimized as $108. लेकिन अभी हमने डुअल प्रॉब्लम सॉल्व किया है और इस डुअल प्रॉब्लम को जो है हम इसके सोल्यूशन को यूज़ कर सकते हैं, एंड यूजिंग द डुअलिटी थ्योरम्स वी कैन फाइंड द सोल्यूशन टू द प्राइमल प्रॉब्लम टू. From the solution we have seen that VA was equal to 1.5, VB was equal to 6 and VC was equal to 0. That is the shadow prices of inputs A, B and C are respectively 1.5, 6 and 0. And we have already seen what is the implication or the interpretation of these shadow prices. Using this and using the duality theorem, where we have said that if the shadow prices, or in this case the shadow prices are representing what they are representing, the choice variables of the dual problem. So if the choice variables of the dual problem are known, we can find the corresponding value of the slack variable or the dummy variable. So यहाँ पे हमारे पास VA is 1.5, VB is 6, that is they are non-zero, they are optimally non-zero. This would imply that the corresponding slack variables in the primal problem, they are equal to 0. And similarly in this case we have found that VC, which is equal to 0, the shadow price of input C is equal to 0. So ये choice variable यहाँ पे जो हमारे पास VC है that is equal to 0. If the choice variable in the dual is optimally non-zero, then obviously its slack variable, its corresponding slack variable in the primal will be equal to 0. लेकिन यहाँ पे हम ये देख रहे हैं कि जो choice variable है that is equal to 0, that is VC is equal to 0. Therefore its corresponding slack variable in the primal problem will not be equal to 0, it will be non-zero optimally. सबसे पहले यहाँ पे आप स्क्रीन पे देखें कि हमने जो हमारा प्रॉब्लम था मैक्सिमाइजेशन का, दैट इज़ प्राइमल प्रॉब्लम, उसको हमने जो है उसमें स्लैक्स ऐड किए हैं सो दैट इट इज़ कन्वर्टेड इनटू इक्वेशंस. जो इसके इक्वालिटी कंस्ट्रेंट्स थे उनको हमने इक्वेशंस में जो है कन्वर्ट किया है बाय एडिंग SA, SB एंड SC रिस्पेक्टिवली टू द कंस्ट्रेंट A, B एंड C. और इसी तरह से हमारा जो मैक्सिमाइजेशन जो ऑब्जेक्टिव फंक्शन था उसमें भी हमने 0SA प्लस 0SB एंड 0SC जो है वो ऐड किए. सिंस देयर कोएफिशिएंट्स आर 0, therefore the objective function will remain the same, that is pi equal to 12x plus 9y. Since we have already said that the choice variables in case of dual problem, that is VA and VB, वहाँ पे हमने देखा they are non-zero, therefore their corresponding slack variable in the primal should be equal to 0. तो इसलिए SA और SB जो हैं वो 0 के बराबर होंगे because these are binding constraints. So now solving these two constraints simultaneously, first two constraints, तो इसमें आप देख सकते हैं first constraint is given as 4x plus 2y equal to 32, and multiplying the second constraint by 2, we get 2x plus 2y equal to 20, and then subtracting the second constraint from the first, we get 2x equal to 12 or x equal to 6, and substituting this value of x into the first constraint, we get the value of y which is equal to 4. So आपको याद होगा कि जब हमने यही प्रॉब्लम पहले सॉल्व किया था तो यहाँ पे जो ऑप्टिमल आउटपुट मिक्स था दैट वाज x equal to 6 and y equal to 4, and producing 6 units of x and 4 units of y, the firm maximized its profit which was equal to $108. So यहाँ पे हम जब इस combination को, which is the optimal solution, x equal to 6 and y equal to 4, when we substitute this into our objective function, we get the same result, that is $108. और इसी तरह से अगर हम third constraint को consider करते हैं, which is equal to 3y plus the slack variable SC equal to 21. So 3 multiplied by 4 plus SC is equal to 21, or SC is equal to 21 minus 12, which is equal to 9. So the slack variable associated with input C is equal to 9, और यही result जो है हम पहले मालूम कर चुके हैं when we solved this problem as a primal problem. लेकिन यहाँ पे जो ये solution हमने इसका अभी आपको find out करके बताया है, we have found this solution, this complete solution of the primal problem, that is x equal to 6, y equal to 4, and the profit is maximized, maximum profit is equal to $108. और इसके अलावा यहाँ पे हमने ये भी establish किया है that the slack variable of the first two constraints are equal to 0, and the slack variable for the third constraint is equal to 9, which means that out of 21 units of input C, only 12 have been used by the firm. The remaining 9 have not been used. So यहाँ पे ये जो solution, इसका complete solution of primal, we have obtained this solution from the dual problem. जो dual का हमने solution किया था वहाँ से हमने आपको ये primal का जो problem, primal का solution जो है वो आपको derive करके बताया है. So in this way we can see that using duality theorems and the information, both of the duality theorem and the rules that by which we transform one problem to the other problem, we can easily find the complete solution of one problem given the solution to the other problem. That is, given the solution of the primal problem, we can completely solve the dual, or given the solution of the dual problem, we can completely find the solution to the primal problem. With that, we come to end of this session. Thank you. Khuda Hafiz.